Okay, so we're doing our first presentation on differential equations, and I'm just going to make this short presentation on what a differential equation is and how to visualize it. A differential equation, well, it's an equation, and it involves a function and at least one of its derivatives. So an example is this. We have the derivative of y minus 2xy squared equals 0. This is a differential equation. To solve a differential equation means to find a function, an unknown function, y as a function of x, that satisfies the equation. And what do I mean exactly when I say that y equals f of x satisfies the differential equation? Well, for example, if we take y equals this function here, negative 1 over x squared, and you plug it into this equation, noting that y prime is 2 over x cubed, and so just plug in verbatim what you see here with y prime and y being replaced. You get this, which is 0, which is why I said that y equals negative 1 over x squared satisfies this equation, because when you plug that function into this expression, you do get left-hand side equals right-hand side. In fact, there are lots of solutions. Here's another one. You can check on your own that this also satisfies this differential equation. And this is often the case. You have infinitely many solutions for differential equations such as. Now, if we rewrite the differential equations, we put the y prime on the left-hand side and the xy squared on the right-hand side. And then suppose we go ahead and graph the solution, this solution, negative 1 over x squared plus 1. It's a bell curve looking thing, upside down because of the minus sign. And if we pick a point on this bell curve, we'll see that the slope of the graph at that point is xy squared, because for the very reason that this function is a solution to this differential equation, and this differential equation says the slope of your unknown function has value equal to xy squared. So for example, if we go over here to the point 2 comma, what would that be? 2 comma negative 1/5, then you would find that the slope is, well, it's a small positive slope. Let's see, negative 1/5 squared is y squared, that's 1/25, and x is 2, so positive 2/25 is the slope at this point. Whereas if we went to this point, for example, then the slope there, well, the point is 0 comma negative 1, and if we plug that in here, we see that the slope is 0, xy squared is 0, and indeed our graph is flat or has a slope of 0 at this point. And you can check that this continues to be the case for any point on this curve, that the slope at the point xy is xy squared. And that's exactly what we mean geometrically when we say that we have a solution to a differential. Now, suppose we mark the slope at any point in the plane with a short line segment indicating the slope. So I have some code that does this. There are details on my website for how to get this function to work. You actually have to download it from my site because it is not a standard Mathematica function. By the way, I will be using Mathematica throughout these videos, and almost all the code that I use to produce the graphics and solve equations numerically when applicable, I will include on the PowerPoints. So here we have, after using these two functions, including downloading this from my website, this produces this output. This is called a slope field, in case you haven't seen one before. Although good calculus classes introduce students to slope fields, but not all calculus classes are good, unfortunately. And if we graph our function, I believe we said it was negative 1 over 1 plus x squared, you see how it has this elegant way of threading through the slope field. So no matter where it goes, it's always moving with the slope field. This is to be expected. It's just a restatement of what I said before, that the slope at any point is xy squared. So that's what a solution looks like when plotted on top of a slope field. Now, clearly there are lots of solutions. If you start at any one of these blue points, you get a different solution that goes through those given points, like so. Alright, so let's discuss a different differential equation, y prime equals x squared plus y squared minus 1. This is an interesting differential equation for reasons I will discuss momentarily, but first let's draw the slope field using the same Mathematica functions that we discussed before. So this is the slope field. It makes sense when you think about it, why it looks this way. If you look at points near the origin, the slope is about negative 1 because x and y are close to 0. Whereas if you move further away from the origin, the x squared plus y squared takes over and the slope gets very positive very fast. So everywhere the slope is positive except near the origin. And now let's actually see what a solution looks like. Unfortunately, so this is what's interesting about this equation, is you actually can't solve it exactly. When I say can't solve exactly, what I mean is you can't find a solution like e to the x or sine of x, or no elementary functions or combination thereof will satisfy this equation. And that's not to say that solutions don't exist, it's just that they can't be expressed in this nice closed format. So we have to numerically solve this differential equation, and Mathematica does have methods of doing that. It's called ND-solve, numerical differential equation solve, I suppose it stands for. You can take a look at this syntax and try to understand exactly what it all means. It's just specifying a differential equation. I also specified an initial value of y of 0 equals 0, basically specifying I want a curve to go through the origin. I specified that the dependent variable is y, and I wanted the independent variable to range from -3 to 3. And then I stored a plot of this solution into this variable called solplot1, and when I plot it all together, what I get is the slope field along with the sol plot, and this is what it looks like. Now it kind of looks like maybe like a cubic graph, perhaps something like y equals x cubed minus x would seem reasonable. But if you plug that into this differential equation, you will find that it's not correct. It does not. In fact, there is, as I said before, there's no solution, polynomial, exponential, trig, that would go through the slope field precisely. So there is no formula that gives this curve, but nonetheless, computers can generate these curves for us readily. So as I said, exact solution found. So going back to this equation, y prime equals xy squared. Now we can find exact solutions to this one, and let me show you how. So we begin by writing it as dy over dx instead of y prime. And this allows us to separate variables. I put that in bold because separation of variables is an extremely important technique in many of the differential equations that we'll be studying. So we're going to bring all of our y's to the left-hand side and all of our x's to the right-hand side, like so. And so we have we've rewritten this equation in this format, and now we are allowed to integrate both sides, like so. And calculating these integrals, both just the power rule and including an arbitrary constant of integration on the right-hand side, and finally solving for y, we get what's called a general solution to this differential equation. So meaning that no matter what value of c you choose here, what you have is a solution. So the different values of c give rise to all these different curves. You can let c be any number, anywhere from negative infinity to infinity, and it gives rise to every single one of these curves you see, except for this flat one corresponding to y equals 0. And there's a few ways that you can think about this. One is to say, well, first of all, let me just point out that this is a general solution almost, in the sense that it includes every single solution except for this one. Now, why did we miss this solution? That's what I'm trying to explain in a couple of different ways. One is that you could say that if you let c equal infinity, and I'm putting that in giant quotation marks because that's not really allowed, but if you let c equal infinity, then you can think of it as meaning that you have y equals 0. And so it's kind of like c equals infinity gives you this curve here. A more technically correct explanation would be to go back to the previous slide and notice that we divided by y squared when we were solving the equation, and hence we eliminated implicitly the solution, any solution involving y equals 0 when we divided by y. So anyway, that concludes this introduction to differential equations, just what they are and how to visualize them. And we also solved one differential equation, and we will be developing lots of techniques for solving more complicated differential equations, and especially solving differential equations that apply to physical situations in the following presentations.